can hear you.
Okay, I will start my presentation. So, hello everyone, my name is Sujeong Lim from Ewha Women's University in South Korea. It is an honor to present my work today, and I will talk about parameter estimation in the land surface model. Land surface model provides surface fluxes as the lower boundary condition for regional enthalpy model and climate model, but it contains uncertain parameters based on empirical relations, so it can resulting in uncertainty in model solution. Such uncertainty can be reduced by estimating optimal parameter value. The parameter estimation is the process of estimating unknown model parameters by feeding the model output to the observation to calibrate the model and gain insight into complex physical processes. Optimization method is one of the ways to address parameter estimation because it automatically minimizes the difference between model and observation and helps replace the massive manual experiment. So in this study, we implemented a global optimization algorithm. The name is microgenetic algorithm into land surface model to find the optimal parameters. First, the genetic algorithm is one of the evolutionary algorithms to search for the best potential solution based on natural selection and the survival of fitness inspired by Darwin's theory of evolution. In particular, the micro-J is a computationally efficient GA with a smaller population. It generates the random population and goes through the fitness evaluation, crossover, ellipticism, and reinitialization to generate diverse potential solutions that refit during the maximum generation. And it is already widely used for parameter estimation in meteorology and hydrology. So in this talk, I'm going to briefly introduce our recent work on parameter estimation in the land surface model using micro-J. The first work is about the snow-related parameters. In the NOAA land surface model, which is a common LSM, there are three snow variables, such as fractional snow cover, snow albedo, and snow depth. And we investigate the most sensitive parameter in this equation like this. We also tested parameter sensitivity to understand the relation between each parameter and its snow variable. Such parameters often reflect the local characteristic where the empirical relations are made, so it requires additional tuning of a parameter when we apply them to other regions. So in this study, we seek the optimal parameter values of snow process in NOAA-LSM solved for South Korea. To get the optimal parameter, we collected in situ observation for snow depth and satellite observation for fractional snow cover and snow albedo. We selected the 25 stations where the in situ observation is located, and they included 5 land cover types. This figure shows that the flowchart of a coupling system of micro-J and NOAA-LSM. Every generation evaluates the fitness function, which determines how excellent or fit the candidate solution is with respect to the predict model within a given maximum generation. So in this study, we define the fitness function as a normalized improvement ratio of RMSE and then average it for 3 snow. We run separate optimization experiment in here using 5 parameters and Wmax parameter because this parameter is only dependent on the land cover type, so we separate 2 optimization experiments. After that, we verified them with the following experiment. CNTL experiment is a control experiment without optimization. PRF5 use optimized 5 parameters, and PRF6 is use optimized total parameter. Table 1 summarizes the optimized snow-related parameter. Within a prescribed range, based on the previous work, micro j finds an optimal value. As a result, the snow variable will increase or decrease depending on the parameter change. Figure 5 shows that overestimate snow albedo and underestimate snow depth, and they are elevated in BRF6 experiment. Table 2 summarizes the improvement ratio of RMSE, mean bias, and coefficient of determination. Except for mean bias for fractional snow cover, most performance were improved. The snow depth in particular has more observation sample than satellite observation, resulting in the greatest improvement. And next parameter is soil texture parameter. Soil texture describes the different grain size of mineral particles, such as clay, silt, and sand. And they are determined by the combined percentage of clay, silt, and sand using a textural triangle having 12 different classes. This soil texture is dominant factor for estimating soil moisture because it can change the airspace, drainage, and water holding ability of the soil. But the problem is that it is hard to measure. So we optimize the percentage of clay, silt, and sand in multiple soil layers to improve the soil moisture prediction. We use land surface model Utopia made by University of Torino. Because this is a multi-layer model, we can divide soil like this. So we divide soil into 9 layers, and each soil layer requires soil texture information. To make a proper soil texture profile, we optimize the percentage of clay and sand. We set the parameter range for clay and sand in 7 soil layers because we assume that the bottom 3 layers had the same soil texture. We also included additional conditions to prevent unnatural soil. During the optimization, as the percentage of clay and sand is randomly assigned, the silt is automatically calculated to satisfy the sum of all soils equal 100%. Micro J repeat this thing until 500 generation and optimize 14 parameters within a potential solution of 2 to the power of 70. So we conducted optimized experiment in 4 stations in Italy where the in-situ observation have sufficient periods and multiple soil layers. To verify the impact of optimized percentage of clay, silt, and sand, we run the following experiment. The first one is HWSD, use the harmonized world soil database, and it provides the percentage of clay, silt, and sand in 2 layers. FAOG use a discrete FAO soil map, and it provides the 1-layer information. INSD experiment used in-situ observation, measured percentage of clay, silt, and sand, but only a few stations have this observation, and measured the soil depths are different. OPTM used to optimize the percentage of clay, silt, and sand. The optimized soil texture was evaluated using soil moisture performance. So we defined the fitness function as a weighted natural Clipper efficiency of soil moisture against in-situ observation. This index is a widely used verification index in hydrologic model. Considering the topsoil layer has more reliable observation, we gave more weight compared to bottom layers. As a result, during the 500 generation, the fitness function converges at their maximum value. So these are the results. When we investigate the soil texture, soil database have a simple soil texture information reporting loam. The in-situ observation provides a percentage of clay, silt, and sand at 10, 20, and 30 centimeter, and they report silt clay loam and clay loam. On the other hand, our OPTM experiment suggests soil texture profile and modifies hydraulic parameter accordingly, so it results in the improvement in terms of RMSE and R. And this is the other station example. Because this station doesn't have in-situ observations, only the soil databases are available. As a result, OPTM suggests soil texture profile and leads to the biggest improvement in 30 centimeter. First layer. Since the deeper soil layer contains uncertain observation, it interrupts the optimization at 60 and 90 centimeter. So as a summary, the average soil moisture RMSE in 4 station shows the smallest RMSE in OPTM experiment compared to typical soil database and sometimes in-situ observation. So it means that when in-situ observation do not exist, OPTM can be more effective than other soil database. And last subject is the soil state perturbation parameter. In the ensemble data simulation system, the ensemble spread, like a blue circle distribution, represent the model uncertainty. If the underestimated ensemble spread occurred, it could ignore the observation information, so it requires the implementation of ensemble spread like left to right figure. A stochastic approach with random forcing can be used to represent the model uncertainty. For example, the stochastically perturbed physical tendency is a famous method to represent model uncertainty by perturbing the parameterized physical tendency. And the underestimation is also found in the coupled land and atmospheric modeling system, especially near the surface. In this study, we assume that under dispersive soil temperature and soil moisture can be a source of an underestimated ensemble spread of temperature and water vapor mixing ratio in planetary boundary layer through the heat fluxes change. Therefore, we developed the stochastically perturbed soil state scheme in YLSM over world. If perturbed soil temperature or soil moisture to represent the near surface uncertainty. For solid state, at the first soil layer, we add random forcing during the every time step. If you see this figure, the ensemble spread of soil temperature is inflated by adding a random forcing. As for the soil moisture, we use bound sets between the wilting point and saturation level, and we do not add perturbation over the snow cover or frozen soil. In this method, the important thing is that how could control the random forcing, because the random forcing is a tuning parameter which is a function of amplitude, decorrelation length scale, and time scale. There are typical scales for atmospheric perturbation, but they were not appropriate for soil states in our study. So we optimized the tuning parameter of random forcing using a coupled system of micro-J and SPSS in the warp ensemble system. Here we designed the fitness function using normalized mean square error, which evaluates the interaction between land surface and atmosphere, especially in the PBL. And based on the previous work and sensitivity experiment, we assigned the parameter range like this. And as a result, we find 4 optimized tuning parameters suitable for soil temperature perturbation in daytime or nighttime, and soil moisture perturbation in daytime or nighttime. Using the optimized tuning parameter, we activate the SPSS key measure inflation method in the ensemble data simulation system. Results showed that the control experiments in black colors showed an underestimated ensemble spread in soil temperature, soil moisture, and temperature and water vapor mixing ratio at 1,000 hectopascal. But when we perturb soil temperature and soil moisture, the following ensemble spreads can be increased. In particular, when we consider the diagonal varied tuning parameter in STP2 or SMP2 colored by red colors, the soil temperature and soil moisture showed good relation between ensemble spread and RMSE. However, when they are propagated to the atmospheric model, the ensemble spread of temperature and water vapor mixing ratio is weakly increased. So this is my conclusion. We introduced the application of a parameter estimation using microGA in land surface model to find optimal parameter. Our results showed that if there are historical observation or reference data to be evaluated, parameter estimation can be addressed with optimization method, but we always care about the optimized parameter should be physically explicable. Okay, thank you for your attention.
Thank you very much for your talk, Sujeong.
Yep.
So let's see if there's any questions. Please write them in the Yopad. Let's give everyone a moment to formulate their thoughts before moving on. But I guess the Yopad will stay available. So Lars has a question. Lars Nigger. Do you know physical reasonable ranges for all parameters?
Yes, actually, that is a very difficult thing when you optimize parameter. So at first, we investigate the previous work based on the sensitivity experiment. So we check that the minimum and maximum range, they are physically acceptable or not. So firstly, we conducted a sensitivity experiment to certain that parameter range is really physically acceptable or not.
Okay. Thank you. So with that, I think this session is also closed, and I'll give the floor back to Tobias.